Thank you for staying for the second talk of today. It's going to be by Ozlem Ergun, who is a College of Engineering Distinguished Professor in Mechanical and Industrial Engineering at Northeastern University. Dr. Ergun's research has focused on design and management of large-scale and decentralized networks. She has applied her work on network design, management, and resilience to problems arising in many critical systems. She's worked with many organizations around the world, and recently she's partnered with the Massachusetts Executive Office of Elder Affairs to help match qualified medical professionals to long-term care facilities with open positions around the state. Dr. Ergun has served as a member of the National Academy's Committee on Building Adaptable and Resilient Supply Chains after Hurricanes Harvey, Irma, and Maria, and the National Academy's Committee on Security of America's Medical Supply Chain. She was the president of Inform's Section on Public Programs, Service and Needs in 2013, and is an Inform's Fellow. She served as the area editor of the Operations Research Journal for Policy Modeling, Public Sector Area, and currently serves as the department co-editor at the EMSOM Journal for Environment, Health, and Societies Department. So prior to joining Northeastern, she was at Georgia Tech, where she was the Coca-Cola Associate Professor, and she co-founded the Health and Humanitarian Systems Research Center there at the Supply Chain and Logistics Institute. She received her bachelor's in, at the time it was known, I guess, Operations Research and Industrial Engineering from Cornell University. Now I think it's Information Engineering when I received it, and a PhD in OR from MIT in 2001.
All right, thank you, Alexander. So hi there, and so this will be quite a different talk, and I think what Vera presented was what I thought I would do for the rest of my life when I was starting the PhD, and I ended up doing something completely different, or completely much more applied. But that was a really, really nice result, Vera. So I will talk about something very applied work, although I hope that you find it somewhat interesting and somewhat innovative in this group. So this is work that I have done around global food aid delivery for USAID. And it's really the main paper of one of my former PhD students who just graduated about 6 months ago, Asia. So just very quickly, I'm going to go through kind of the introductory materials very quickly since we don't have too much time. Food aid, global food insecurity is a big challenge. It has a huge scope. More than 70 to 90 countries get food aid every year. And unfortunately, because of different challenges, the kind of the scarcity of the resources keeps increasing. So the main objectives when we work with food aid delivery humanitarian organizations are threefold. One is cost efficiency, obviously. So we try to maximize the use of available resources to serve as many beneficiaries as we can. But at the same time, there's also the question is on-time delivery, which is a big deal. And then the third one, which is really the focus of this paper, and it has not been maybe discussed too much in humanitarian operations literature, is that there are multiple classes of disasters or events that happen where the humanitarian organizations have to respond to. And what I mean by that is that usually, especially in food aid, there is some sort of a set of demand that kind of occurs every year, kind of pretty much regularly, and their level is somewhat either forecastable or, you kind of know, like Ethiopia is always going to need at least this much amount of food, right? Or this kind of food. On the other hand, there is also kind of sudden onset events that create huge demand spikes, and they tend to be kind of like not known in terms of when it will happen, where it will happen, or what kind of commodity it will require to respond to. And in most of the research that you see in this area, what you see is that people usually either focus on either ongoing or sudden onset disasters and response operations. On the other hand, really thinking about these operations together creates a lot of opportunities that can increase the on-time delivery and the cost efficiency of the operations. So that's what we will be looking at today. So I have worked with the what used to be USAID for over multiple years, and they had a huge project, like three-phased project that was called Food Aid Quality Review, and we ended up coming in the third phase, and we were focusing on supply chain optimization part of it, and we work with them very closely. So we have quite a lot of data. We had some things that gotten implemented and so on and so forth. So the work that we did, part of it was descriptive data analysis. We had about 8 years of data in total that we looked at. And the idea of this descriptive data analysis was really trying to point or find smoking guns of improvements. And then we focused on what can we do to kind of create an optimization framework, or like what are the types of optimization problems that we should really concentrate on, given what we have seen in the data analysis. So we had two papers out of this. One was really looking at end-to-end operations and kind of trying to figure out efficiencies, do some policy analysis, and that work got published in Inform's Journal of Applied Analytics. And then what I'll talk about today is really this last paper, which is looking at this strategic decision making, but really thinking about both ongoing and sudden onset response. So I just want to talk about a little bit of the network that we're dealing with, the global network. So what we have here is first, this is USAID, so all supply comes from the US or used to come from the US by congressional mandate. So the first leg of this, or the first echelon of this network, was really sending supplies from the suppliers all over the US to US loading ports or warehouses within the US. Then the second kind of part of the network, or the second echelon, was sending things from the US to international ports and warehouses. And then finally, usually what happens is, like, you send the demand the commodities that's at the international ports or warehouses into final delivery countries. So you can even look at more in a more focused under a more detailed way, and the network, what happens once the commodity enters a country, and the last mile. That's what we did in the first paper, but in this paper, we're just looking at this more simplified network, which has 3 echelons. Okay. And then, so as I said, we're really looking at both forecastable ongoing demand, and then we're not even going to worry about forecast accuracy or anything. We're just going to say we kind of know what's ongoing demand is going to be like. And then we look at the sudden onset demand, the first stage decisions that we're really, the strategic decisions we're focusing on, where to open warehouses, to store safety stocks and preposition inventories. And then the second level of question that we're looking at is the levels of the safety stocks that we want to keep for rapid response to sudden onset demand. The objective is to minimize total cost, or total expected cost, which is the fixed cost in the first stage, plus the second stage operational cost based on where you opened up your warehouses, where did you put your safety stocks, and what kind of commodities did you choose in that safety stock. And then we also want to minimize demand response time. As I said, we have data, about 8 years of data, and our really focus has been on the methodology and kind of coming up with a new data-driven framework, instead of we look at kind of 2-stage regular stochastic programming kind of a formulation and analysis. What we have done is we created this data-driven framework that we call scenario-based decision learning, where we basically create thousands of scenarios using the data that we have, and then we solve the problem, the optimization problem per scenario, and we get thousands of optimal solutions, and then we try to make sense of those optimal solutions. Okay, so I'll get into this a bit more. Um, so, so just kind of going back to the historical demand data, what we had, as I said, we had about 8 years of data. However, we knew from the from our interactions that the data contained both ongoing demand, response to ongoing demand, and sudden onset demand. However, this was not labeled. So we didn't really know what USAID know or did not know, or when did they know. So it was kind of like all this operational data and demand data, but no one had labeled it as like, oh, this was a sudden onset event. So, so what we needed to do was kind of first to kind of figure out how do we label this data, and then we had to kind of, obviously model the operational realities. And there, what we did is the following. For ongoing demand, which we assume to be forecastable, or you can even call it deterministic, operationally, we could do regular procurement, plus we could add proactive planning, which is advanced purchasing and prepositioning. So here we kind of know what we need to serve, but then we also know the cyclic nature of prices and capacity availability of both commodities and the transportation. So it still makes sense to do some advanced purchasing and prepositioning. So it still makes sense to have warehouses where we actually store inventory before distributing it. So the ongoing demand was served in that operational framework. And then the sudden onset demand really responded to these rare events. And the way that you could respond to that was you could do proactive planning. And in this sense, the proactive planning I'm going to call the safe to stock. So this was really kind of allocated inventory to only respond to rare events. It's separate from the advanced purchasing that we did, which was still also in inventory, but that goes for the ongoing demand. And then we had to and then operationally, we could also do reactive procurement, which is after the fact, after a disaster, we could procure and send things to the country. Yes, I have a question.
Yes, it seems that within sudden onset demand,
Mm-hmm.
there are different levels of unpredictability. So, hurricanes are disasters, but you have some idea of how many you're going to
Yeah.
have per
Mm-hmm.
year. Other things, like USAID funding suddenly getting cut off at the whim of
Yeah.
one person who shall remain unnamed, seems a lot less predictable.
I mean,
You categorize within that sudden onset demand sort of different levels of
mm-hmm.
infrequency.
Well, I mean, it's a good point. You're definitely right, and you can even talk about, what is the forecastability, right? Like even if you have an estimation of hurricanes, and then you wouldn't have an estimation of earthquakes, right? Or like a hurricane, you kind of know it's coming within a few days of it's happening, and then earthquake, it doesn't. So there's a lot more fine planning and modeling that or intelligence you could put into this for sure. But it's not here in this model. But you're definitely right. That's when you start doing more kind of more operational planning, I think you would have to think about those. I do see even in strategic planning that, yes, you do have some sort of, so what I would say is some of the things that are uncertain, but somewhat, like the hurricanes or kind of the drought that you almost always have in certain parts of Africa, those maybe you kind of think about as ongoing demand, that you have a kind of some level that you have to serve. But I mean, you're right. You could do much more fine kind of classification of demand here, right? And we only classify into two.
Okay, thanks.
Thank you. Okay, so I'll continue. So now getting into some of the modeling parts, like I will not show you anything that's very mathematical, but I just want to kind of give you a taste of what we did. So for responding to sudden onset demand, we create this response network, and mostly this sudden onset response network is like a path formulated network flow. And the reason that we use path formulation here in the sudden onset demand response network is because there are a lot of constraints in like how you can serve, when you can serve, and you have to make sure that you're not doing things in your optimization problem that kind of anticipates that there will be an sudden onset event. So we kind of completely depend on a path formulation here that puts in a lot of kind of special constraints and just incorporates it into the path generation process. And furthermore, we only do limited path generation in all stages of the supply chain, just because otherwise everything just explodes. And there are usually good constraints and operational knowledge where you can limit your path generation. So in having said that, in the sudden onset demand, we do limited path generation to represent reactive procurement from US suppliers to the final delivery countries. We also do limited path generation for proactive safety stock shipment from the warehouses into the final delivery country. So this is like where you actually build the safety stock. And then we also do limited path generation for the reactive inventory replenishment. So what this means is that we force our model to replenish whatever safety stock it uses, because otherwise it's in a way not fair, right? Like you have to kind of, if you're keeping a certain safety stock level, you also have to make sure that once you use it throughout your planning horizon, you have to replenish it within a certain time period. Okay, so we create all of this planning through limited path generation. So our response network looks something like this. And then we integrate that with with the formulation for the ongoing demand, which is arc-based actually. And so again, like, don't look at the math. There's kind of the formulation, which is kind of straightforward. There is nothing that's just so strange or complicated here. We have flow balance constraints, storage capacity, vessel capacity, supplier capacity. The only things that are somewhat interesting are these non-anticipativity for sudden onset operations. Again, you have to kind of be very careful in terms of how you write these constraints so that you're not allowing your math program to kind of start doing stuff before a sudden onset, like not mobilize anything before a sudden onset event happens, right? So then, we do the safety stock levels, and then so the one thing that we have to make sure is that the safety stock, as I said, is only limited to be used by sudden onset. And then there is one other constraint that I haven't mentioned yet, which is the warehouse related cost budget. And this was when USAID was operational, there was usually a mandate in terms of not allowing money spent too much on like safety stock or even advanced purchasing. So this is kind of like the government being, or any kind of a humanitarian organization being, risk averse and saying like, I don't want to buy too much for something I don't know yet, which is not very, I'll show you that it's not a very good policy, but it is there. So then the question is, obviously we have a stochastic program in front of us, and many times what kind of the straightforward approach to this will be to say that I'm going to use the historical data as my scenario. So if I have 8 years of data, I'll have 8 scenarios, and I'm going to solve a two-stage stochastic optimization problem where I have 8 scenarios. Obviously, this is a very limited demand set. It doesn't necessarily capture all the rare things that can happen. And then if you try to generate more scenarios, right, and put it in again into this two-stage stochastic optimization framework, then computationally these are very large problems, and it becomes very, very hard to solve them. So what we do is this. So this is the classic stochastic optimization framework. I'm sure for this audience, it's very straightforward, right? Like you kind of make your first stage decisions of opening warehouses, deciding on safety stock levels. You have your scenarios generated, and then you kind of solve it over all your second stage decisions over all the scenarios, and then you get an expected total cost. So for our problem and our formulation, for only 8 historical scenarios when they were used, just to build the model, we were taking about 2 hours, and then the solve time was about 10 hours. And then when you increase the scenario count, everything was just kind of halting as expected. So compare that to this kind of very naive approach where we say, like, I just generate thousands of scenarios, and then I solve for each scenario the optimal decision for both the first stage and the second stage decisions. And then I get 1,000 optimal decisions for each of the scenarios, right? So when you do this, what we get, as I said, we get thousands of solutions, optimal solutions for these thousands of demand scenarios. And for 1,000 set of scenarios, the model build time, and which we do only once, is about 20 minutes, and we solve each scenario in less than 5 seconds. For 1,000 scenarios, you require about an hour and a half only. And then there is no exponential growth if you increase it from 1,000 to 2,000 scenarios. It's kind of linearly increasing. So what is our proposed framework is the following. So we have the historical data. First, we do cleaning and all of the things you would do with real world data. And then we use some kind of a deep learning model to label our data, saying which ones are sudden onset and which ones are ongoing demand. And then use the labeled data to actually come up with a model, like a generative model that actually now generates scenarios that are coming, like that have the same type of characteristics as our historical data. And then what we do is then we have the labeled historical scenarios, we have the generated scenarios, and what we can do is we can then compare just kind of stochastic programming outcomes with the scenario-based decision learning outcomes. And then the other thing that we really kind of push or kind of talk about in this second setting is that what we have is now also we can think about the demand futures that derive different types of optimal decisions. So what we have is now we can say, like, okay, let's look at all the decisions we came up with, 1,000 different decisions, right? With our approach, we can now cluster these based on the decision characteristics. So, like sets of scenarios lead to similar decisions clustered in many clusters. And then we can also come up with demand futures that are kind of readily available, and then we can extract and build demand futures. And then we can say, okay, let's match the demand futures to the decision cluster. Which kind of demand futures define the decisions in a different cluster? And then that helps us to both interpret what the decisions are driven by what kind of demand futures. So, and then potentially this can even kind of become a decision support tool, in the sense that if someone comes to me and says, like, I don't know what's going to really happen, but on these futures, I kind of have a sense, then we can actually even say, like, maybe for the next year or next couple of years, we should actually have this strategy for opening warehouses and safety stock levels, because your kind of prediction falls into this cluster. Right. So what we like about this kind of framework is that it gives us a bit of an interpretability of why certain decisions are being made in this or suggested, right? So we have a bit of time, so I'll talk about a little bit of results. So if we just did the stochastic optimization, two-stage stochastic optimization with the 8 scenarios, what we see is that if we have a budget on the warehouse locations, then we only open up 4 locations with 4 different commodities in them. And then when we relax the budget, we always add more warehouses in the US. So having more warehouses in the US is always operationally and in terms of response a very good thing. But because US is very expensive, this is very expensive. So whenever you have a budget constraint on the warehouses, you never open up anything in the US. So what does that mean in terms of kind of metrics that we would be interested in? So we look at 3 cases. The first one, we actually do not allow any proactive strategy for sudden onset demand. And then we have 2 other cases where like we have a budget basically on the warehousing costs. And then in the second one, we have a much larger budget, or you could even think about this like no budget on the warehouse cost. And what we see is that having this proactive strategy of keeping safety stock to serving sudden onset demand is very effective, both in terms of demand fulfillment ratio, meaning that it actually, like your fulfillment ratio goes from 78% to 98%, and then the average response time goes down from 79 days to 46 days. However, of course, your cost per unit delivered goes up. You are doing more, so you're paying more. So the other interesting thing that goes from having a budget limit on your kind of proactive operations for sudden onset demand actually decreases the cost while also increasing the fulfillment ratio and then decreasing the sudden onset response time. So it's really, as I said, and this is like I have done this work with World Food Program as well. It's always good to have a huge budget for these kind of proactive events that are very rare and undeterministic, like really rare, not coming from usually from a distribution. So it's actually good to be risk-taking most of the time. But then what I'll show you is what happens when we now look at the solutions that we create based on the framework that I described. So what we do is we solve for 1,000 scenarios, and then we basically look at the frequency of warehouses being opened. So what we see is, for example, this is just one computational example, is that there are in 4 different regions of the world, we get some warehouses gets opened basically almost all the time, which really corresponds with what the stochastic optimization solution shows. So for example, in East Africa, you always open Djibouti and Mombasa in almost every single scenario. And then things start getting a little bit more interesting in terms of the distribution of which warehouse you open in West Africa, South and West Africa, South Asia, and you almost never open anything in America. This is with the budget constraint. Things become more interesting without the budget constraint because you have more feasible solutions, basically. So things get more diverse. Yeah, so like this is kind of what warehouses gets most frequently opened. We can also look at, sorry, I'm rushing because of the time. We can also look at patterns, like those were like single warehouses that are getting opened. We can look at which patterns get opened. And it's interesting to see that the stochastic optimization solution sometimes appears as a pattern that gets opened for one of the scenarios, but then sometimes it doesn't. Like here, when you don't have the budget constraint, the stochastic optimization solution doesn't even exist in as an optimal solution to any of the solutions. So, and I'm gonna just skip this. We don't have time for this, but what I want to show you is basically at the end, what we see is the key insights that we get is when we do our framework, it really improves on cost efficiency compared to stochastic optimization framework, which is this column. And it also improves on kind of the 3-period fulfillment. As you can imagine, right? Like you push things maybe more towards more frequently observed demand patterns, sudden onset demand patterns, but it doesn't really improve on the late delivery penalty or average response time. On the other hand, if you do have this luxury of kind of identifying demand futures, and you can base your decision based on these demand futures, then you do actually get significant improvements on kind of like serving fast and responsiveness, but you don't really do better in terms of the cost per delivery. So I'll stop here.
Thank you, Ozlem. I think that just because of the interest of time, we will shift all of the questions to the breakout rooms, which I'm about to open. But thank you all for coming, and for both you and Vera for your very nice talks, and related in some conceptual way at least. We're going to have our next dots in a month from now, and stay tuned for the email announcing that. So thank you all for coming, and stick around for the breakout room.